Hey guys, I apologize for my voice a little bit as I'm fighting a cold, but I wanted to get you these dilation and similarity notes. So let's start with dilations. So dilation is a transformation that just changes the size. All things about the shape will stay the same. So a triangle will still be a triangle. It's not going to get taller or wider. It's just going to get bigger or smaller. The way that it changes is called the scale factor. The way to find the scale factor is to take the image and divide it by the pre-image. I'm going to move myself over here so you can see this. The scale factor determines whether or not you're getting bigger or smaller. A reduction is going to mean that your scale factor is between 0 and 1. So it's going to be a decimal that starts 0 point, or it's going to be a true fraction in which the numerator is smaller than the denominator. An enlargement means that the k, the scale factor, is going to be greater than 1. Now at any time, if you need to pause the video to write down what you see on the screen, please do, as I'm offered a limited amount of time that I can record. So these two triangles that you are seeing are created by a dilation. We have our pre-image triangle here, A, B, C, and we have our image after the dilation, A prime, B prime, C prime, remembering that the prime means that a transformation has occurred. So now, if I want to figure out what the scale factor is, let's go back here, I can remember that it's the image divided by the pre-image. So I take values off of the image and divide them by values off the pre-image. So in this case, let's take a value, make sure that I'm connected here. Let's take a value off of the image. Remember, this is the image. So let's say the distance from A prime to B prime. So from A prime to B prime, that was 12. So I take the matching AB, and that gives me 4. Divide them, and that gives me 3, which is my scale factor. So I have a scale factor of 3. This means that every number in the original image, since it is greater than 1, was enlarged 3 times. So 4 times 3, 5.5 times 3, 5 times 3, and you can see 5 times 3 gives me 15. 5.5 times 3 gives me 16.5. So this was your first Plicker question of the day. And it asked if the points B, 2, negative 5, and A, negative 1, 3 were dilated to create B prime at 6, negative 15, and A prime at negative 3, 9, what was the scale factor of the dilation? You had your choices here. Now you automatically could have eliminated A, as we are not dealing with negative scale factors. That causes kind of an inversion to the problem. So I see that I started with 2 and negative 5 and then moved up to 6 and negative 15. Some of you are going to be able to just look at that and know what the scale factor is. But remember, the way we can find it is to take a value from the image and divide the equivalent value from the pre-image, and so I can see that the answer is 3. Here's another question. Under what dilation, under a dilation where the center of dilation is the origin, the image R negative 2, 3 and is R prime negative 8, 12. So this dilated to become this. So what I'm asking is what would be the coordinates of n prime if n was 1, 4 and it's the same dilation? So once again, I would need to see, well, what was the scale factor? I had negative 8. That originally came from a negative 2. Again, the negative 2 dilated to become negative 8. So I take my image, divide my pre-image, and that gives me a 4. I can see the same thing here. 3 times 4 gave me the 12. So if I multiply 1 by 4 and 4 by 4, you can see that you would get 416. Okay? Now let's talk about the center of dilation that was referred to in that previous problem. Center of dilation is a fixed point about which all points are enlarged or reduced. Now, this figure on the right has a center of dilation right here. The reason I know this is because they share that vertex. It's kind of like when you're doing a computer program and you draw a shape. If you grab the corner, see this little corner with the line here? If I grab that one and size it, it stays in proportion. Its center of dilation being this vertex right here, because no matter what size I make it, that vertex is staying consistent. Okay? So that's how I know that this is my center of dilation, because no matter how big or how small it is, that stays the same. Now if they're not attached, overlapping each other like this, or if they're not touching a vertex, the way to find the center of dilation is to start with the bigger image and draw a line. Let me use actually my line tool here. Oops. Is to draw a line that goes through the equivalent corresponding vertice of the other one, and then just extend a little bit further out. Because what you're looking for is you're looking for a point of intersection. And as you see with this last line here, again, big through the small, and then extend out, you can see that I have created a point of intersection, and that point of intersection is the center of the dilation. So here's a few other examples here. So we've got these two shapes, and this is on a grid, so we can actually find the official value. Get my tool again. So I can start at the big, go through the equivalent vertice of the small, and extend out. Big through the small, and extend out. Big through the small, and extend out. And I could do this one, but as I can see, this line kind of took care of it. So it looks to me, my lines could be a little off, but it looks to me that they intersect at right about -4.5. Alright, so our next problem here, we can see that they are inside of each other, but they're not sharing a vertice. So I would still need to draw my lines in order to see where the center is. Now some of you might be able to eyeball this one, but let's play through it. Start at the big, go through the small, and extend out. Big through small, extend out. Big through small, and extend out. And as you can see, it's almost right there, dead center, which is, as I can see, is on the x-axis and the y-axis. So more than likely, that center of dilation is at the origin. Next problem. They share a vertex, so nothing I need to do. I can see right there that they have a center of dilation at 3,1. Whoops, make the other one go away. So here I've got a couple of lines. Lines are still shapes, which means they still have a center of dilation. And so again, big through small and extend. Big through small and extend. And I can see that they also are at the origin. Alright, that's center of dilation. Alright, so here I've got your next Plicker question that you answered in class. And I see that segment HA is going to be dilated from the origin, that's the important part, by some scale factor that would cause a reduction between 0 and 1. So which of the following must be true about the final image? So the key phrase there is that it's dilated from the origin. That means that my lines would have intersected at the origin. So I can see here if I extended out and went in kind of the opposite way, since I already know where the center of dilation is, I know that every line I created, regardless of whether it was getting smaller, like this, or bigger, like this one, would all fall underneath kind of this triangle, this expansion here. So that means no matter if I'm getting smaller or if I'm getting bigger, these segments are not going to leave this second quadrant, which means all of the x values would be negative and all the y values would be positive. Now, dilation notation. This is a very common notation. However, this notation is only dealing with a center of dilation at the origin. So D for dilation, a subscript O for origin, and then you would be given the scale factor. You would take your coordinate and just multiply the scale factor. Simple enough. Now let's say, though, that the center of dilation is not at the origin. What you're going to do is follow a simple process, 3 steps. 3 steps. You're going to subtract the center, then scale it by multiplying the scale factor, and then you're going to add the center. Now, I know sometimes there's a little logo here. You may not be able to see it, but we'll get to a problem in a minute, and hopefully that'll work out better for you. So let's start with just some simple notation. Again, all of these are centered at the origin, so all I have to do is multiply the scale factor. So if I take -2, 0, and I multiply each by 3, I would get -6, 0. 0. If I took these and I am multiplying by a scale factor of 0.5, so that would be 5 times 0.5 and -8 times 0.5. That would give me 2.5 and -4. This last one I'm multiplying by a scale factor of 1. So 1 times 4, 1 times 3. Doesn't change anything because a scale factor of 1 means it didn't get enlarged, it didn't get reduced. It stayed exactly the way it was. Alright, let's move on to the trickier of the bunch. So in this problem, it's not being dilated at the origin. It's being dilated at some other location. In this particular problem, it is being dilated at 2, -3. So that's the center. So let's go through the steps. Step number 1. I start with my original coordinate, which was -4, 2, and I am going to subtract the center. All right, subtract center. So the center was 2, -3. So if I subtract it, I'm subtracting 2, and I'm subtracting a -3, which really means I'm doing the opposite, so plus. And that makes -6, 5. Step 2 is to scale it. Well, it had a scale factor of 2, so I'm going to take this coordinate and multiply everything by 2. Times 2, times 2, and that will give me -12, 10. Final step is to then add the center. So again, the center was 2, -3. I'm adding. So adding a negative is really just subtracting. And so that will give me -10, 7. So -4, 2 with a scale factor of 2 centered at 2, -3 turned into -10, 7. Alright, so that was dilations. You should have a practice worksheet you can find on Canvas. And we'll move on. Next lesson is similarity. Another video.